To achieve success in financial markets without luck, someone needs to understand the basics of the framework, including math. So in today's video, we'll be exploring how math and finance are closely intertwined, more than you might think. In around 600 BC is where we start our exploration, with Thales of Miletus in ancient Greece. He was a mathematician and an astronomer, and he wanted to show that his research was actually important, so he turned to financial engineering. Now watch closely, since the market manipulation he pulled off so early in history is pretty impressive, and Aristotle actually recorded this feat. Thales predicted when it was winter that the following spring would have an abundance of olives from his astronomy research. So he ensured that he had control of all of the olive presses. Then when the abundance of olives came and everyone wanted presses, he rented them out at any rate he wanted. Aristotle actually said that this was proof that philosophers could easily become rich if they wanted to, they just chose not to. And this is how Thales pulled off one of, if not the, first call option contract in history. Now we jump to 13th century Italy to Fibonacci. You might know him from the famous Fibonacci sequence. 1, 1, 2, 3, and so on, adding all the numbers together. He solved more complex numbers with interest rates and investment returns, and he also pondered questions like this one, which I've translated into modern English. 20 shirts are worth $3 total, and $42 of toilet paper are worth $5 total. How many rolls of toilet paper for 50 shirts? Feel free to try this with modern algebra techniques. It should not be that difficult, but back then it was harder. Skipping forward in time quickly, we go to another gambler studier, Cardano. He was a leader in probability theory, and he led the framework for Blaise Pascal and Fermat, two famous mathematicians who 100 years later pondered this problem. Should you bet on the occurrence of at least one double six with 24 throws of 2 die? You can try to solve it if you want. A previous mathematician thought the answer was no, but he realized that mathematically he was wrong. Using probabilities, Pascal and Fermat were the first ones who came up with rudimentary derivative pricing models. Now we go to the more interesting stuff. Bernoulli studied the following riddle. Suppose that you flip a coin. If it's heads, you flip again, and if it's tails, then you stop. And you continue this process until a tail is rolled, so this for example. If only one head total was rolled, you get $1. If 2 heads were rolled, then a tail, you get $2. If 3 heads in a row were rolled until your first tail occurred, you get $4. If 4 heads were rolled, you get $8, and so on. Continue this process into infinity. And what would you pay to be able to play this game? Bernoulli found that theoretically, your expected value should be infinite money, and so you should be okay with paying any amount to play. Of course, in the real world, everyone knows that you wouldn't pay $1 billion to play this game, and if you gain an intuition of how this problem works, you can clearly see how it goes into infinity. So mathematically, you should. So what's the discrepancy? Bernoulli found that nobody would play this game at a high price, since earning 100 trillion instead of 50 trillion does not significantly improve quality of living, as much as 100 versus 50. And besides, earning 100 trillion, that's crucial for the valuation of this game to be going into infinity, is nearly impossible in the real world, so the game's expected value solely lies within the theoretical. You would likely pay only $20 maximum to play such a game in the real world. Now meet this famous mathematician. He used the mathematics of Brownian motion to apply trajectories for modeling stock price dynamics and calculating option prices. Brownian motion is physics and math study that models the randomness of particles. It's really effective in stock market since the market is essentially a random walk. You know how Robinhood tells you statistics when you buy options? They use the Black-Scholes model, and this mathematician created the precursor. Norbert Wiener aided this. In 1827, he observed rapid oscillatory motion of microscopic particles in a fluid that resulted from their collision. But these particles could also represent stock market price with stochastic or random mathematics of oscillation. It's interesting how two seemingly unrelated fields, finance and physics, correlate so closely. Now we go to arguably the cornerstone of financial mathematics, the Black-Scholes model, a beautiful intersection between probability, calculus, and finance to take in parameters to price options. I showed it earlier, and it is a wonderfully complex function, published by Fisher Black and Myron Scholes, and supposedly discovered earlier by famed hedge fund manager Ed Thorpe. It determines so much in our markets and deserves a video on itself, so make sure to subscribe to see a complex function reduced into something understandable. Much research nowadays goes into shifting around the many parameters, assumptions, and conditions of the Black-Scholes model to make it fit to certain scenarios, and that is just a brief surface of the beautiful intersection between math and finance.